All right, so we started talking about regression. So we focused on the simple linear regression, which is of this form. So you have data xi's, these are your independent variables, and you have response or dependent variables yi. And you want to determine these parameters alpha and beta, and this and the main reason this is a challenge is because there is always random error. And I gave this example where relative humidity and moisture content is measured from samples, and this was in the Mathematica file, and I'll come back to this example today again. Okay, so in fact right away. So the aim is to determine estimators for this A for alpha, B for beta, and we use this method of least squares to calculate or to determine formulas for these estimators. And in the example we determined these values, and we next wanted to determine the distributions for these random variables estimators, assuming now that the yi's, the errors are IID, the errors are so the errors are IID normals with mean 0 and variance sigma squared, and therefore the responses are means with normals with mean alpha plus beta xi and variance sigma squared. So they are not IID because the means are different, but they are independent. And so we had certain assumptions, and we determined, of course, A and B are linear combinations of normals from the formula, and therefore they are also normals. So we determined the mean for B and showed that it's an unbiased estimator for beta, and we also determined its variance. So now I want to show you something which might have escaped your attention. So okay, let me go back to this file. So this is the relative humidity, this is the x-axis, and or the independent variable, and the moisture content in the sample, which was dependent variable. Oh, okay, so I've done something. So we reload this. Okay, so I cannot use m now. Okay, so I have to change this. So let me call it m1. Okay, so we had done the least squares estimation, and we had found this curve which fit this data fairly well. But I want to I want to show you something which you might not have realized, which is that what if we reverse? Okay, so let's go back to the example. So back to example. So what if we reverse the roles of xi and yi? So what, I mean, just as a thought experiment, let's say yi's are the independent variables and xi's are the response variables. Let's just suppose. Okay. So in that case, so let's go back to the formula for B. So this is the formula for B. So all I have to do is to, there was another formula for B. Yeah, this one. So all I have to do is to, in calculating B, I have to reverse the roles of x and y. Right? So here is the formula. Look at the numerator. It's symmetric in x's and y's, so that is unchanged. And the denominator, I just have to replace x's by y's. So let's do that. So this is the new estimator. So now instead of so the numerator is unchanged, and denominator, instead of RH of I whole squared, I have m1 of I whole squared sum, and instead of n x bar squared, I have n y bar squared. Okay, and I calculate it, and I similarly calculate a by again interchanging the roles of x and y and using the new b. So I have x bar minus b y bar. So that's that. Okay, so now, so then you know, if what you want to say? So if so now I want to compare this data. So if y is a plus bx, then x is minus a by b plus 1 by b y, right? Just interchange. B is not 0, so not a problem. So I look at minus a by b and 1 by b. So these are the intercept and the slope respectively. And now I plot, so I'm using y just to, I'm plotting this function as a, with calling this y instead of x, just to remind you that I'm doing it in the reverse order. And now you look at this plot and you see it's also a good fit. But are these numbers the same? So these are my replacement for a and b. Right? So let's compare. So a was, sorry, I should look at the old a. So the old a was minus 2.51 and the new a is minus 3.96. The old b so the old b is minus 3.23, sorry, 0.323, and the new b is 0.354. Okay, so now b, the new b, which is 1 by b, 1 by this, maybe I'll call it b prime. Oh, sorry, not 1 by. Is 0.354, and new a, which is minus a prime by b prime, is minus 3.96, which is different. From old A and B. I mean, these numbers are different. This looks like a fairly good fit, but so does this, right? So why is this happening? Why are we getting different answers in both the cases? Anybody?
Sir, I suppose in one of them we are trying to minimize the square of the vertical distances, and in one we are trying to minimize the square of the horizontal distances.
That's right. Yes, Prithu is on the mark. So when we talked about the least squares estimator, let me go back to that. So we were minimizing this quantity, but this is, as Prithu correctly points out, this is the vertical distance. It's yi is the, okay, so let me go back to the plot. So yi is this point, and a plus b xi is, yi is this point on the y-axis, and a plus b xi is this point on the y-axis. So we are minimizing vertical heights, right? And when we flip the roles of x and y, we are minimizing the horizontal heights, horizontal line squares, sums of squares. Okay, so there is a lack of symmetry, and this is not completely unreasonable, because one is a dependent variable and one is an independent variable. So you should not a priori expect any symmetry, but this is something to notice. And okay, so this is because we were minimizing vertical sum of vertical heights, height squared earlier, and we are minimizing sum of horizontal height squares now. Okay. Alright, so this is one point I wanted to make. Okay, so let's get back to our agenda. So we
Excuse me, sir.
yes.
So, what should we plot on the y-axis usually?
The usual dependent variables are plotted on the y-axis. That's response variables. That's the usual convention. Okay.
No, my question was whether we should be minimizing the horizontal distance or vertical distance.
No, vertical distance. The least squares estimator it minimizes the vertical distance. Okay, and we'll see today why that's the right thing to do. Okay. So so back to our program. So we have seen that b is a normal variable. So to determine the parameters for normal, we need its expectation, which we showed to be beta, and variance, which we showed to be this formula. I will. So let's do this for A. So now let us just determine the distribution for A. So what was the formula for A? Let's go back there. So since A is y bar, which is 1 by n sigma I yi minus b x bar. So the randomness is only in the y's and therefore consequently in the b's. In the b, sorry. Yeah. So this is also a linear combination of normals. So which is just like B, also a linear combination of normals. A is also a normal. So A is also a normal random variable. So let's calculate its expectation. So again, we need the expectation and the variance. So then expectation of A is 1 by n sigma I, linearity of expectation, remember, sigma expectation of yi. X bars are fixed quantities, so x bar expectation of B. But yi's are normals with mean exactly alpha plus beta xi. This is precisely what it is. And expectation of beta we have already calculated to be B. Expectation of B we have already calculated to be beta. So minus x bar times beta. Okay, so now you see what's happening. So the first term is alpha n times and there's a 1 by n, so I get an alpha. The second term is beta times sigma xi by n, which is just x bar. And this quantity is also beta x bar. So they cancel and you get alpha. So you get that A is also an unbiased estimator. For alpha. So these are good estimators. I mean they have mean equal to the parameter that we are looking for. Okay, and we can also compute the variance, which I leave for you as an exercise. Show that variance of A is sigma squared I xi squared divided by n times sigma I xi square minus n x plus. This quantity we will define very soon. Okay, so you can use this the same formula. We know variance of b, we know variance of yi's, but b and yi's are not independent. So you have to be a little careful in this calculation. So I leave it for you to check. Okay, this is so please do that. Okay. So we have talked about so far we have talked about estimating the unknown parameters alpha and beta, but we also have sigma as an unknown parameter. How are you going to estimate it? Okay, so let's talk about that. So recall. So this is a new topic. So recall that the residuals are yi minus a minus bxi. This is precisely the vertical distance in the graph that we were talking about, where yi's are independent. Okay. Yi's are normal alpha plus beta xi sigma square, and a and b as before. Right? They have these somewhat complicated formulas. So we'll construct the sums of squares of residuals as before. Sum of squares of residuals. We'll call it now SR. So sum over I, yi minus a minus bxi whole square. Okay. So you see what is happening here. These are normals, and you are subtracting one more normal, and which is a, and xi times another normal. Right? So we are summing these quantities. So we are kind of taking out, in some sense, the mean, and in some sense, we are normalizing the variance. So again, I leave it for you as a computational exercise to show that SR by sigma squared is a chi-squared random variable, i.e. a chi-squared random variable with n minus 2 degrees of freedom. So remember when we were talking about the sample variance of normal data, if that was S by sigma squared was a chi-squared random variable with n minus 1 degrees of freedom, but now we have n minus 2 degrees. And remember what is chi-squared? It's sums of squares of standard normals, so many of them. Okay, so I mean, all you have to do is to show that this quantity, this sum will give you n normals, and this a and b will sort of take off 1 degree of freedom each. That's the intuition behind why you have n minus 2 degrees. Okay. So this is also something that you can show. So assuming this, the expectation of SR by sigma squared is n minus 2, right? Because it's a sum of n minus 2 standard normals, squares of n minus 2. Okay, and therefore, if I, flip things around, SR by n minus 2 has expectation sigma squared, and therefore is an unbiased estimate. I mean,
So
yes.
can you please explain how SR upon n minus 2 is also an unbiased estimator?
Because it has expectation sigma square. I mean, I just take this around. These are numbers, right? I can pull it out.
Yes, yes.
Okay. So here is here's a remark. Which you might use freely. So it turns out we will not do this in the class, but one can show that SR is independent of the pair AB, and this is similar in spirit to the fact that S squared, the sample variance, is independent of X bar, the sample mean, for normal data. So the proof was, I mean, we had to do some, I mean, this was some work to prove. So this is something I don't want to spend too much time on. But a similar, the same kind of thing holds here also. And this is maybe not too surprising because we are assuming normality of errors and so on. Okay. Okay. So, any questions? Okay. So let us now talk about the maximum likelihood estimators. So MLE for alpha. So we constructed A and B as least squares estimators. For alpha and beta, respectively, right? Remember what we did. So let me go back here. So we took this S, which I'm calling SR now, sums of squares of residuals, and I just without motivating it too much, I just said the standard ways to use this method of least squares, and then we did the usual trick, took the partial derivative, etc., and we found A. Right? So, but you might complain that that was a bit ad hoc. I mean, who told you to do that? Just I mean, the honest ways to do is to look at the maximum likelihood estimate. So let's do that. Okay. So look at, so now we look for the MLEs. Okay. So recall that the likelihood function aka the joint density is what? It's f y1 up to yn of small y1 up to small yn, the arguments. This is by independence product over I, f sub yi of small yi. And what is the is the density for these guys? The yi is, capital Yi is a normal with mean alpha plus beta xi and variance sigma square. So we know the density of the normal. So it's 1 by 2 pi e to the minus y minus a plus or minus bxi whole squared by 2 sigma squared, right? And so combining these factors, I need some space. So let us write here. So this is 1 by sigma to the n, 2 pi to the n by 2. Let me write it as x of minus 1 by sigma squared, 2 sigma squared, that's common. Sum over I. Oh, that should be a yi, sorry. Yi minus a minus bxi whole square. Okay. So what do? We oh sorry, what am I doing? This should be alpha and beta. Okay. So we are constructing these guys, and now you see. I mean, what's the usual way? We want to maximize with respect to alpha and beta, and you know, a standard trick is to take the log, so which we call the log likelihood function. So but what happens to the log likelihood function? If you take the log of this, you get yi minus a minus beta xi whole squared sum over I, and some factors extra, right? There's an additional sum of a constant because of this, and you know there's a proportionality, but all that is not going to matter. I mean, the log likelihood function is essentially proportional to SR. This sum of squares of residuals that we just defined. I mean, what we are going to do is differentiate with respect to alpha and beta and call the and solve for them, for these equations, and call them A and B. But that's precisely what we have done here. What we have done earlier. I mean, we didn't call them alpha, beta. We called them A and B, and we differentiated, and we said we calculated. So therefore the maximum likelihood estimator is also the least squares. Okay. So this example that I did earlier today, I mean, this is not a flaw. This is part of the system. I mean, this is the way. It's a what's it called? It's a character. No, it's a trait, not a flaw. The fact that you are going to get different estimators when you switch x and y is part of life. I mean, it's just something one has to live. Okay. So to answer Soham's earlier question, we should take the vertical distance squared, and that is the correct thing to do. Okay. All right. Okay. So right now I'm going to move towards the questions of hypothesis testing. So for that, it will be convenient to define some notation. So define the notation. The following notation. So let me call S small x capital Y to be the sum over I xi minus x bar times yi minus y bar. And this we have shown to be equal to sum over I xi yi minus n x bar y bar. So I'm writing x in small and y in capital. I hope it's so. I hope you see how to get this. I mean, the first term will give you this, and the last three terms will all give you this. Two come with a negative sign, one comes with a positive. So, what does this quantity remind you of? Anybody?
Covariance.
Covariance, right? This is like the covariance. So, not exactly the covariance, but this is like the covariance. And Sxx will be sum over I, xi minus x bar whole squared, which is summation over I xi squared minus nx bar squared. And similarly, Syy, this is sum over I yi minus y bar whole squared, and similarly this is sum over I yi squared minus n bar squared. Okay, so these two are like the variance. I mean, not exactly, we are missing one by n minus. So then the MLE or B squares estimator can be written as what? So let's first write B. B was what? So let's go back here. B was sum xi yi minus nx bar y bar, but you can see that's exactly this quantity. So B is Sxy in the numerator divided by sum xi square minus nx bar square, and that's precisely Sx. And A, well, A is just that. Okay. So that was already earlier. Y bar minus Bx bar. Right? So, so in terms of these quantities, we have shown that B is a normal random variable. What was its so what was its expectation?
Beta.
The expectation of B was beta. Yes, exactly. And the variance, if you look at in terms of this is sigma squared divided by Sxx. Right? So B is a normal random variable with mean beta and variance sigma squared by Sxx. And A is a normal random variable, which we did earlier today. Let's look at that. So A has mean alpha and variance this complication. The numerator we can't do more than write it in that way. I mean, you can write it in terms of Sxx with some correction, but the denominator is precisely n times Sxx. Okay, so A is a normal with mean alpha and variance sigma squared sum over I xi squared divided by n Sxx. Okay. Okay. So now let's look at SR. Moreover, SR is sum over I yi minus a minus bxi whole squared. And now I substitute a and b using this notation. So this is sum over I minus a is what? A is y bar minus bx bar, and b I will substitute this. Okay. So it's y bar minus b, which is sxy by sxx b. Sorry. x bar, right? That's A, minus B, which is again Sxy by Sxx xi, the whole thing whole square. Okay, so this is A and this is B. Right? Everybody is okay with that? Okay, so now you see there are two kinds of terms. There's yi minus y bar, and there is, okay, so maybe I'll write it step yi minus y bar minus Sxy by Sxx xi minus x whole square. Right? So xi comes with a negative sign and x bar comes with a positive sign. So I'll write this square as this squared plus this squared minus twice the steps. Okay, is all of this inside the sum? So sum over I yi minus y bar whole squared plus Sxy by Sxx whole squared xi minus x bar whole squared minus 2 times this times this. So Sxy by Sxx yi minus y bar xi, sorry, small x xi minus x. Okay. Now let's do the sum. What is this first sum? Summation I yi minus y bar whole square.
It will be SYY.
Thanks. That will be exactly SYY. Now let's look at the second term. The second term, this is a constant, so I pull it out. So Sxy whole squared divided by Sxx whole squared. Then what is sum xi minus x bar whole squared? That's precisely Sxx. So one term cancels, one Sxx cancels. Minus 2 times, this is a constant, Sxy by Sxx. And now what is this term? This is precisely Sxy. Okay. And now if you notice carefully, these two terms are the same. So this is Sxy squared by Sxx. This is minus 2 Sxy squared by Sx. It's the same thing with an opposite sign. So this is precisely Syy minus Sxy whole squared by Sxx. And to write it more symmetrically, this is Sxx Syy minus Sxy whole squared divided by Sx. So this is a formula for SI. Okay, should have moved. Oh, sorry. Oh. Sorry about that. So that's a compact formula for this. So let's again verify this in Mathematica. Okay, we have proved it, so nothing to verify, but it's just. Okay, so Sxy was the sum over xi minus x bar times yi minus y bar. So in our example, it's this. Sxx is sum over xi minus x bar whole squared. Syy is sum over yi minus y bar whole squared. And let us check that B, so I said, let's check these two equalities. So B, I mean, as it is will not be true because I changed B to mean this. So let's redefine B and A. And so then I check that B is Sxy by Sxx and A is y bar minus B times x bar. This is kind of stupid to check because I defined A this way. Okay, and this SR, which is sum of squares, is this, and let's check that SR is Sxx Syy minus Sxy squared divided by minus Sxy squared divided by Sx. That's standard. Okay. Well, so things work as they should. Okay. So now let's talk about the inference problem. So we want to do hypothesis testing for our parameters. Okay, so the first non-trivial hypothesis for our simple regression it is y is alpha plus beta x plus e, is the error, is to check that beta equal to 0. Okay, this is the first non-trivial thing you can do, i.e. the response is independent of the input, or equivalently there is no regression of y on x. And this reminds me, let me go back to our first example. Let me rewrite this. So here y, okay, the regression of y on x is different from that of x. Okay, so this terminology is asymmetric. This is something. Right? So that should reinforce this. This terminology should reinforce the lack of symmetry. Okay, so no regression of y on x means y simply does not depend on x. If beta is 0, y is just alpha plus some error. Right? Okay, so let us see how to check this. So to check this, we will need the distribution of b and sigma square. So we have shown let's go back here. So we have shown that b is a normal with mean beta and variance sigma squared by sxx. So b minus beta by the square root of this quantity is a standard normal. So b minus beta by square root of sigma squared by sxx, which is the same thing as saying square root of sxx b minus beta by sigma squared is a standard. Right? Oops, sorry. Okay, my n is horrible. So if we know sorry, is there a question?
So shouldn't it be sigma instead of sigma square in the denominator?
Oh, sorry. Thank you. Thanks. So if we knew sigma, then we could. I mean, all of this is coming from data. I mean, b is known from data, sxx is known from data. If we knew sigma, we could estimate beta, but we don't know sigma, right? So this this problem is related to a problem of estimating the mean when we don't know both the mean and the variance, right, for normal data. So this is similar to that. And SR by sigma squared is a chi-squared random variable with n minus 2 degrees of freedom. And both are independent. Yeah, just a second. Well, we have shown in question. I mean, these two things I have. This I've left as an exercise, and this I have stated without proof. Yes, so.
Sir, haven't we assumed a value of sigma so that sigma is known to us?
No. Where have we assumed sigma? So, when we calculated, okay, let me go back to previous class. So, when we gave these formulas for A and B, they were purely in terms of data. Right, so B is, I gave formula B here and A here. This was purely in terms of data. Right? So we
Yes.
did not need to use anything about sigma because we were just constructing the estimators. Then
Okay,
when
so
we looked at the distributions, we saw that the distribution, the variance, both are normals. The variance depends crucially on sigma, but we don't know sigma.
Okay, sir. So we have just said that the error term is a normal with variance sigma square, but like we haven't assumed any sigma square for that error.
No, and I mean, experimentally there are ways of measuring the error. You perform a bunch of, I mean, you do what, there's a term for this. You set up the system. Calibration. This is called calibration. You calibrate your instrument by performing an experiment to which you already know the answer, right? And that will tell you. When you do the calibration, you will find statistics for the error, and you can sort of sometimes use that as your proxy for true error. Right? So that one can. Okay. So right. So now I ask you, what distribution? I mean. As I said, this is similar to the problem of estimating the mean, let's say confidence intervals for the mean of normal data when you don't know the mean and the variance. So what test will we, or what distribution will come up now?
T distribution.
That's right. Yeah. So, so therefore, because of this independence, which I stated as a remark without proof, therefore, the ratio of what? The ratio of this divided by square root of this divided by the number of degrees of freedom, which is n minus 2, will be a t random variable. So the ratio, which is square root of sxx b minus beta by sigma divided by the square root of SR by sigma squared n minus 2. This is a t random variable. So let me simplify something. So this sigma will cancel this sigma squared. And so I'll write a square root first. I'll get n minus 2 sxx by SR. That is all inside the square root, and then I only have a b minus beta. Is a t random variable with n minus 2 degrees of freedom. T random variable, say Rv, with n minus 2 degrees of freedom. Right. So exactly like before. Okay, maybe this is a good time to stop. I should have been promising to leave you 5 minutes earlier. Um, so so next time we will talk about confidence intervals and hypothesis testing for B and then for beta and then also for alpha. Okay. Any questions? Okay. Let's stop then and see you on Friday.